Good day, and welcome to CFE Media's Virtual Training Week. For this session on how to engineer a secure industrial control network, we'll be joined by Richard Wood, Product Marketing Division Manager with Moxa. I'm Kevin Parker, an editor with CFE Media and Technology. Following our presentation, be sure and stay tuned for the live Q&A. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. The threat landscape for industrial control systems continues to grow, making it a rising concern in most organizations. Typically, these networks have evolved over years or even decades, with their design predominantly focused on safety and reliability. In this session, the presenters will outline the current threat landscape, identify some of the most common vulnerabilities, and outline some practical first steps to take to secure industrial control systems, as well as how to take a more holistic view of ICS security. Here are some of today's learning objectives. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you would like to take notes within the session, click on the left panel labeled Notes to do so. Please remember that this session will be made live at 12 p.m. Central, 1 p.m. Eastern. The question and answer session with our industry expert starts approximately at 12:45 p.m. Central, 1:45 p.m. Eastern, or immediately after the presentation ends, if it runs a little longer than 45 minutes. Answers will be archived with the session. You can see the Q&A details in the meeting tab on the left side of the screen. Zoom invite details can be found in the additional resources tab under Q&A session. Want to take this session again? No problem. This session will be available on demand. If you experience difficulties, please log out and back into the session to continue. Attendees are eligible for 1 PDH credit for this event, airing on March 30th, 2021, and is categorized within the technical, health, and safety, including core technical category, or RECEP. Before turning to our presentation, we'd like to share a brief video from today's sponsor. Welcome back. I'd now like to introduce today's speakers. Richard Wood has worked in industrial automation for more than 25 years, working with plant and process engineers, systems integrators, and original equipment manufacturers to implement reliable, efficient manufacturing systems. For the past 6 years, Rich has worked with OT professionals to address challenges in deploying secure, connected automation and control networks. Richard, welcome to our virtual training week session, and please go ahead.
All right, thanks, Kevin. Hello, everybody. Let's start by reviewing today's learning objectives. First, we'll review some of the threat history and common threats. Next, we'll discuss some of the main differences between IT security and OT security. We'll cover some of the most common vulnerabilities and then start addressing them with some practical first steps in securing your ICS. Finally, we'll discuss the use of standards to build up your security capabilities and discuss resource planning and a maturity model. So let's start with some history here. Targeted attacks on critical infrastructure have been occurring since around 2003, but really only started ramping up until around 2010. The hacker groups behind these attacks were usually sponsored by nation states. They built device-specific exploits to inflict significant damage to power companies and other critical infrastructure. Consequently, critical infrastructure operators have paid much more attention to OT security in the past 10 years compared to other industries like manufacturing. However, in the last couple of years, we've been seeing more and more breaches on smart factories. Damages from these breaches, like the 2018 WannaCry attack on chipmaker TSMC, have reached into the hundreds of millions of dollars. But even so, we're still non-targeted attacks, like worm propagation. Only in the last few years have we started to see targeted attacks on smart factories, like the ransomware LockerGaga that hit Norsk Hydro in 2019 and cost them around $40 million in the first week. Let's take a look at some of the other notable breaches. In 2010, the Stuxnet worm targeted industrial facilities running SCADA systems via their unpatched vulnerabilities. In 2015, Black Energy and Kill Disks were malware that deleted all the data and master boot records and caused a 6-hour power outage in the Ukraine, affecting hundreds of thousands of residents and taking over 6 hours to recover from. In 2017, Triton, a Trojan, manipulated industrial safety systems and shut down an industrial plant's operations. Think over the key takeaway here is that if you've been delaying investing in a security strategy because you think your business is not a target for hackers, you could be in for an expensive lesson, as hackers have now found ways to monetize breaches through targeted ransomware type attacks. In taking a look at the overall threat landscape in the US, this chart from ICS CERT breaks down all of the incidents reported in 2016 and categorizes them by threat vector. You can see that phishing, weak authentication, and network scanning were the top threat vectors. Another thing to note was that 28% of these incidences, there were not enough information to determine the source of the threat, indicating weak or non-existent security processes. Unfortunately, ICS CERT stopped publishing this data after 2016, or I'd have more recent statistics. So this brings to light the importance of taking a holistic approach to cybersecurity, considering the aspects of people, process, and technology. As you can see here, the breaches highlighted in the previous slide fell pretty evenly into these three aspects. People tend to think about the technology around cybersecurity, but don't realize the importance of the other two aspects. It's just important to train employees to recognize that a suspicious email or thumb drive found in the parking lot could be an intentional exploit meant to do damage to the organization. Similarly, developing security processes such that patching and upgrading firmware and software or backing up configuration files play an important role in a mature security posture. So now let's take a look at some of the differences between IT and OT cybersecurity. There are some fundamental differences between IT and OT, beginning with their business priorities. While IT professionals typically prioritize confidentiality of data, OT professionals' main concern is safety and availability. In an OT setting, a breach doesn't only risk confidential data, but could also result in injury or even loss of life, in addition to damaging expensive equipment or shutting down the factory. Another key difference is the physical environment. While IT infrastructure is typically in a temperature-controlled data center, OT infrastructure is often in harsh environments where the components are subject to extreme temperatures, shock, vibration, and electrical spikes. The equipment used in OT needs to be built to be able to perform in these kinds of environments. Another big difference is the actual targets of a typical attack. On the IT side, we're typically looking at Windows computers and servers, Whereas on the OT side, you have both Windows and non-Windows devices to consider. In addition to Windows HMIs, workstations, and SCADA servers, other targets include controllers, PLCs, edge Linux computers, meters and sensors, as well as networking equipment. Many of these devices have direct or indirect control over physical assets, so interfering with these devices could result in injury or death, not to mention equipment damage and lost production. So when looking to protect these devices and systems, there are three building blocks of security: authentication, encryption and segmentation, and detection or protection. Authentication is determining if you are who you say you are, and should you have access to what you're trying to access. In general, we try to follow the least privileged methods, meaning that we grant only the minimum access required to get the job done. Encryption and segmentation are the next building block, and this is about data protection. Generally, you want to limit where data can travel on the network to only where it must travel to perform the intended operation. If data is transmitted over open parts of the network, encryption ensures that it can't be intercepted and tampered with. Encryption of management sessions ensures that usernames and passwords can't be compromised. Finally, detection and protection would be the most advanced pillar. While the other two building blocks are aimed at keeping hackers out of the network, detection and protection are measures taken to root out malicious activity that's already made its way into the network. Think of it as an immune system for your network. A common question that inevitably comes up is how much security is appropriate for my network? So this graph is a good starting point for discussion. Deploying security protections is a balance between risk reduction and cost, and involves implementing security protections until some acceptable level of risk has been achieved. Determining acceptable risk involves looking at the probability of a breach, as well as the potential impact of a breach. In looking at the graph here, you can see at the left-hand side that there are some fairly low-cost protections that significantly reduce risk. As you deploy additional protections, the risk reduction decreases, making some of the more advanced protections only appropriate for systems that have much higher probabilities of a breach or high consequences, such as, say, a nuclear reactor or offshore oil rig. In this section, we'll look at some of the common concerns and vulnerabilities in ICS networks. Let's start with some of the most common vulnerabilities reported to ICS CERT over the past 10 years. Historically, the majority of ICS breaches have been the result of an easily exploited vulnerability. Some of the most common low-skill attacks include execution of a non-authenticated control command that either provides a path for a denial of service attack or provides direct access to critical control piece of equipment. The next common attack involves unsecured web services, where credentials are passed in plain text over the network where they can be intercepted and used to gain further access to the control network. Finally, many industrial devices can easily be rendered inoperable by simple buffer overflow. Now let's look at some of the top OT security concerns from this IDC survey from 2020. One of the major concerns is a lack of security expertise. This IDC survey found that over 50% of companies have integrated their IT and OT systems, but 70% of them are still relying on IT team to support OT security. The risk here is that IT security solutions are not easily adapted to OT applications because OT security requires them to consider and fully evaluate the protocols, encryption methods, interoperability, connectivity, and compatibility. Additionally, there are many legacy systems and applications in the OT environment that are not even capable of running an IT security solution. Next, we see that more and more connected assets are being deployed on a production site that often still have the default username and password configured. This puts these devices at risk from both external and internal tampering. The fourth concern is that OT networks utilize a variety of industrial protocols and assets, which means it's a highly heterogeneous environment. This makes it very hard to manage from a cybersecurity standpoint. The last concern is availability has been the main priority for OT network design. This often results in a single, flat, wide open layer 2 network to ensure data transmission without latency. Without segmentation, though, if there's a breach, the threat can spread throughout the entire control network. Here's a summary of the top OT vulnerabilities that we'll address in the next section. The first is low network visibility. Many OT networks have been pieced together over years or even decades, and often do not have an accurate inventory of what is and should be connected to the network. It's not uncommon during an audit to find unauthorized devices or even unsanctioned connections to the network. We've already talked a little bit about weak authentication. Use of default usernames and passwords and shared credentials creates a big risk. It's not uncommon to open a control panel and find a sticky note with a username and password for the device stuck to the inside of the cabinet door. This is kind of like leaving the keys to your house in the front door. We also touched on insecure network design with the prevalence of flat, wide open layer 2 networks. We'll talk about some ways to address this in the next section. And finally, OT networks are subject to insider threats. Employees, contractors, and vendors often have access to the network for a variety of legitimate reasons. USB thumb drives, contractor laptops, and remote connections are all possible ways that malicious code can find its way into the OT network. So now that we've looked at some of the threats to a typical OT network, let's look at some of those relatively low-cost, high-impact things that you can do to increase your security posture. From a high level, we're going to look at security controls from three different aspects: security management, secure network design, and device security. These are all elements of the IEC 62443 family of industrial cybersecurity standards that we'll talk about later in the next section. As we discussed earlier, many ICS networks have evolved through a series of upgrades or projects spanning years or even decades. It is common to find that nobody has an accurate inventory of what is and should be connected to the network, and audits often turn up unknown devices and connections to the network. From a security standpoint, a good starting point is identifying what is connected to the network so that you know what you're trying to secure. A very useful tool in starting this process is to use network management software. There are several industrial-focused NMSs available, ranging from quite inexpensive up to tens of thousands of dollars. But all of these tools have a discovery utility that will scan the network and identify connected devices. They typically will display an inventory report after running this discovery process. This report uses SNMP, or a simple network management protocol, to provide a lot of useful information, such as IP address and MAC address, and even model name and firmware version, depending on the data available from the device's public MIB file. Most of these tools can also automatically draw out the network topology so that you can easily see how the devices are connected and get a sense of the architecture of the network you're trying to secure. It's quite common at this point to see that the architecture is rather random. And here's where, those devices that you weren't aware of, or even connections that you weren't aware of, turn up. While these software titles have many additional capabilities, most people find that the time they saved in the initial audit of the network more than pays for the investment in the software. So once you know what the network looks like, now you can start to design it with security in mind. In general, there are three things that we recommend you look at first. First, segment your network into logical zones so that if there is a breach, it can be contained to a single zone rather than being able to spread throughout the entire network. Second, use industrial firewalls to filter out unnecessary traffic on the network. Unlike an IT network, the devices and protocols flowing over the network are predictable. Eliminating unnecessary traffic can cut way down on the attack vectors used to exploit your ICS network. And third, encrypt site-to-site communications and any other remote access connections to ensure somebody can't eavesdrop on these communications to gain access to the network. Let's look at these three in a little more depth. The concept of zones and conduits is introduced in the IEC 62443 Industrial Security Standard. This involves the segmentation of the network into logical zones of devices with similar security requirements. This could be a single piece of equipment, a production line, or a section of the facility. These zones are then connected by conduits that allow traffic to flow between the zones. The interfaces of these conduits are typically terminated by firewalls, which allow you to define that zone-to-zone interaction. Only specific traffic can flow across these boundaries. Applications which must use these conduits must be examined and their network requirements identified so that they can operate in this secure environment. The diagram here shows network segmentation according to the Purdue model, network levels. Interaction between zones are defined such that levels 1 and 2 can communicate directly, but level 3 cannot directly access level 1. Note that there's a DMZ or demilitarized zone between level 3 and 4, which is the bridge between IT and OT, and that prohibits direct access from level 4 to level 3 or below. The need to control these interactions between zones and limit which protocols can be used over these conduits brings in the need for an industrial firewall. Another concept that we'll discuss is referred to as defense in depth. To illustrate this concept, I like to use the analogy of a medieval castle. A castle has multiple layers of defense that serve to restrict passage in and out of the castle and slow down attackers so that they have time to react to the threats. This might include a moat around the perimeter of the castle, followed by the outer wall, then an inner wall, and finally the towers. The crown jewels are typically hidden in the towers, where invaders must get through many lines of defense in order to capture them. We will employ this same methodology to the network, setting up multiple layers of defense with our most critical assets protected by several layers of security. Industrial firewalls are an important tool in segmenting the network and providing this multiple layered defense. Industrial firewalls have unique capabilities to identify and filter industrial protocols. Some of the industrial protocols in use today were designed at a time when security was not a big threat, and so they don't have security measures built into the protocol. This makes it relatively simple to intercept a packet and change the command from, say, a read command to a write command, which effectively changes the programming in the PLC or controller. Industrial firewalls that perform deep packet inspection can filter commands with these industrial protocols and keep this from happening. Industrial firewalls also provide denial of service protection. Some of the more advanced firewalls will also provide intrusion detection and protection capabilities that use signatures to identify and filter out malicious traffic, much like antivirus software on your PC. These firewalls are then placed between the IT and OT network boundaries to serve as the first layer of protection. Additional layers at the zone and cell levels are added as necessary. When using industrial firewalls, there are two main methodologies that can be employed: whitelisting and blacklisting. The difference is simple. In whitelisting, you define the traffic you want to allow, and everything else is blocked. Blacklisting is the opposite. You define the traffic you don't want to allow and let the rest through. Due to the consistent and predictable nature of an industrial control system network traffic, the whitelisting methodology should be employed. Unlike a typical IT network, an ICS network is relatively static as far as the devices that are connected, which devices talk to which devices, and the protocols being used. It may take a little work to determine and map these data flows and whitelist what should be considered normal traffic, but this approach is very effective. Most ICS networks will have the need for some type of secure remote access. In automation networks, we see two distinct requirements. The first is the ability for two sites to have a constant on network connection, linking services and data between them. This LAN-to-LAN connection typically uses an IPsec VPN connection to encrypt the data between these two sites. Again, industrial firewalls typically have the ability to create this encrypted connection. There is often also a need to provide on-demand network connectivity to support remote users, vendors, or contractors for maintenance tasks. On-demand secure remote access can be accomplished using an industrial firewall to set up an open VPN tunnel into the network. OpenVPN is typically used for these connections due to its ease of use and ability to work through corporate firewalls without requiring IT to open additional ports. If you think you'll need to manage multiple remote connections, there are also cloud and gateway solutions available that give you more flexibility and security in managing multiple connections. Moving on to device security, we usually start with authentication, the process of verifying that people and devices accessing the network are who they say they are and actually have the authority to access what they're trying to access. I'll break this down into two types of authentication: device authentication, which is the use of access the device in order to configure it, upgrade firmware or patches, and do backups. The other is user or network authentication, which is used to make sure the device or user has permission to communicate over the network. Both make use of usernames and passwords to authenticate. It's advised to enforce the use of strong passwords, limit failed logon attempts, and automatically log out users after a period of inactivity. While you may already be used to these practices with your work PC, this needs to be configured on most industrial devices. If you have a larger network or many users, deploying centralized authentication can make managing all of these usernames and passwords more simple and allow for single sign-on. The next best practice in device security is disabling unused and unencrypted management interfaces. Disabling unused logical ports just limits the ways somebody can exploit the device to access your network. By using only encrypted management interfaces, you reduce the risk of someone who's sniffing the traffic on the network to gain access to your username and passwords. Generally, you also want to limit the number of sessions or logged-in users to a device. This prevents the device from becoming overloaded by login requests. Another best practice that can dramatically reduce your risk of a breach is ensuring that all of your devices are running the latest firmware or software. You probably have noticed that your PC regularly asks you to install updates to the operating system, drivers, and applications. Security patches are one of the big reasons for these updates, and they're just as important on your industrial devices as they are on your PC. The reason these are not typically done automatically is because generally you want to test these updates before putting them into a production environment to minimize the possibility that the update might break something. Finding the latest firmware or software is usually as simple as going to the manufacturer's website and downloading it. Once you have tested the update, you can deploy it to the devices in your production environment. Some manufacturers can even alert you to a software or firmware updates via RSS feed or email. Since most industrial networks have many devices from many different manufacturers, it's usually a good idea to check sites like ICS CERT from the Department of Homeland Security, which aggregates known vulnerabilities for ICS devices and gives you instruction on how to mitigate these vulnerabilities. You can sign up for alerts from this site as well. It is common in ICS networks to have PCs, controllers, or other critical devices that cannot be updated, either because the manufacturer no longer supports the product or because upgrading would risk breaking something. Consequently, there are a lot of industrial PCs running outdated versions of Windows, such as Windows XP, Windows 95, or Windows 7. These all have known vulnerabilities without patches, and this is a risky situation for sure. In this situation, you can protect these critical devices by using a form of intrusion protection called virtual patching. Virtual patching utilizes an inline IDS IPS device that uses digital signatures to identify and block traffic that looks to exploit these known vulnerabilities. This can be a simple yet effective way to protect these older PCs and controllers. So the last thing I want to talk about involves people and process more so than technology. Most companies will grant ICS network access to employees, contractors, and vendors for a variety of legitimate purposes, such as maintenance, upgrades, troubleshooting, etc. These people may then use their own equipment, such as laptops or removable media, to connect to the network. These devices could inadvertently infect the network. In fact, this is how the International Space Station, the world's best example of an air-gapped network, was infected by an astronaut who brought an infected laptop to the station and connected it. To protect against these types of threats requires a combination of security process and people training. People need to be trained to understand what activities could pose a risk to the ICS network, such as connecting unscanned laptops, removable media, or even cell phones to the network. There have been several instances where plugging in a cell phone to a USB port in order to charge it has introduced malware into the network. Combine this training with some secure processes to address these risks, such as providing dedicated equipment used for these purposes, scanning all devices with antivirus software before connecting, and disabling internet and email connections from the ICS network are a good start. Many companies will also disable unnecessary USB ports on ICS networks as an additional precaution. So now that we've discussed some of the practical first steps towards securing your ICS network, let's take a look at how you can approach industrial cybersecurity in a more systemic way, leveraging best practices through the use of standards. Thankfully, there's no shortage of standards and best practices to reference when looking to develop your security policies. This chart illustrates some of the more common standards we see referenced in ICS networks. The thing to note here is that while they all have slightly different focuses and scopes, they all have a lot of overlap. Some general purpose standards like NIST 800 take a broad approach by defining desired outcomes, where others like IEC 62443 dive deeper into the details of how to deploy security and how much security is appropriate based on the acceptable level of risk. In fact, NIST 800 lists IEC 62443 as an informative reference. Other standards are specific to a particular industry, such as NERC-CIP for the power industry. I recommend starting with a standard that most closely matches your business. Let's take a deeper look into some of these standards. The NIST 800 cybersecurity framework defines a 5-step approach to cybersecurity: identify, protect, detect, respond, and recover. Within each of these steps, they break it down into more detailed categories. This standard is more descriptive than prescriptive in that it defines desired outcomes. It also lists informative references that are meant to help answer the questions of how to go about securing your network and how much security is appropriate. Two of these informative references are the NIST special publications, SP 853 for Federal Information Systems and SP 800-82 for Industrial Control Systems. These informative references apply the framework to more specific applications and provide a model for similar systems. The NIST 800 framework and these informative references are available for free and can be downloaded from the NIST website. I provided specific links on the slide deck here. The next standard I want to look at is the IEC 62443 family of standards. This is also referred to as ISA 99 or ISA 62443, as the standard started development with the ISA as ISA 99 and was later adopted by the IEC as IEC 62443. You can see here that the family is broken up into 14 standards covering 4 categories, starting from general standards, policies and procedures, system design, and finally component requirements. Note that the top 2 categories pertain predominantly to the asset owners of the ICS networks. The system level category pertains to those who are implementing the systems, such as systems integrators or contractors. And the component category really targets component manufacturers to ensure that they are putting the right security features into the products they're selling to build up secure ICS networks. These standards get very specific. Let's take a deeper look into how things are structured. The IEC 62443-1-1 standard defines 7 functional requirements that are used throughout the body of standards: access control, use control, data integrity, data confidentiality, restricting data flow, timely response, and resource availability. These 7 requirements make up the foundation for secure networks. It also defines 5 security levels that can be selected based on your specific tolerance to risk. Security level 0 means no specific requirements. This is where most ICS networks start out. From there, you can select a targeted security level, and the standard will guide you on what you need to do to achieve this target. Security level 1 guards against coincidental or accidental violations, which itself would have prevented a lot of the reported breaches. Level 1 is typically a good short-term target and potentially a baseline for non-critical parts of the network. For most manufacturing environments, security level 2 is a good target and protects against intentional threats from hackers with low resources and motivation. This describes the bulk of the hackers out there, and achieving this level is quite doable without a full-time cybersecurity team. When looking at levels 3 and 4, we typically see energy companies operating offshore rigs, infrastructure organizations that operate power grid control centers or large generation facilities looking at these levels of security. A lot of these organizations have been focused on security for a decade or more and already have a fairly advanced security posture. These types of organizations have very high consequences for a breach and some well-organized hackers trying to get at them. As I've mentioned, once you select a security level, IEC 62443-3-3 takes the 7 functional requirements and breaks them down into 51 system requirements, then tells you which ones apply to the security level you've selected. It should be noted that it's common to have different security level targets for different parts of an ICS network, with the more critical parts of the network having higher targets than the general network. It is also helpful to know that the security levels build upon the previous levels. so that as you move up in level, you are adding security protections to the ones you've already put in place. All in all, this is a pretty detailed standard that really gets into the nuts and bolts of ICS cybersecurity. I've provided a link to the IEC 62443 Quick Start Guide for your reference. The full text documents for the standard can be purchased from either the IEC or ISA websites for a reasonable fee. So finally, let's wrap things up with a little bit about resource allocation and a maturity model. This maturity model from ARC Advisory Group walks through a typical steps taken as an organization progresses through the development of their cybersecurity program. It also considers people, process, and technology aspects of cybersecurity. You can see that some of the things that we talked about today, like access control, device hardening, and firewalls, fall into the early steps of secure and defend. From a security management standpoint, we started looking at building up capabilities around asset inventory, risk assessment, vulnerability management, and remote access. As you can see, there are a lot more steps to consider as you build up your security posture, but you can expect that it will take time, people, and resources as you move from left to right. Note that the first three steps highlighted in blue correspond to reactive strategies, while the last two highlighted in orange refer to proactive strategies. The things we talked about today can typically be accomplished with part-time people and limited resources initially, but you should think about moving towards dedicated people and resources as your security posture matures. In the later stages of this model, companies typically have dedicated teams of people focused on security. What we've seen to be most successful is when organizations build these teams with a combination of IT and OT personnel and consider all three components of ICS security: people, process, and technology. So this concludes my presentation. I'd now like to open things up for questions.
Well, thanks, Richard, for a presentation that was about one of today's most important issues, but at the same time included a lot of good practical information. Questions will be answered in a live Q&A on April 2nd at 12:45 p.m. Central, 1:45 p.m. Eastern. Participate in the live Q&A with your Zoom invite details. These details can also be found in the Additional Resources tab on the left-hand side of the screen.